Hi, today I'm going to be talking about rotations in Unity. Now, rotations are one of the more complicated concepts to understand in Unity, but very important for many gaming situations. So the one thing about rotations in Unity is that you really have to understand rotations in order to get them to work right. There's a lot of functions that Unity gives you, and unlike some other concepts, you really can't use trial and error to figure out how to get them to work. There are a million ways that rotations will not work, and it's really hard to understand when you see how it's working to figure out what's going wrong. And so you really have to understand the actual math behind the rotations in many cases in order to get them to work right. Now, the math can be hard to understand. It sometimes involves some trigonometry, and I know trig scares a lot of people. It is a more difficult concept to understand, but it is very important to understand the math behind rotations in some cases in order to figure out how to get them to work right. So, in this tutorial, I'll start with the basics of rotation of an object, and I'll dive into using Lerp and Slerp, which are really linear interpretation of rotations. Some of you may have used it on a vector, and you can also use them on rotations. So I'll be showing some examples of how to use those in order to rotate objects in your program. So let's get our programming glasses on and take a look at some code. All right, so for this demonstration, I've set up this basic Unity project. Now, whenever I'm trying to understand a concept, it's always nice to set up some basic test scene that you can kind of play around with the functions and see the results in very straightforward manner, so you can really wrap your head around exactly what's going on when these functions are being called. So essentially what I have is I have a circle, and these represents 10 degrees, 20 degrees, 90 degrees, 180, basically a circle. And I'm going to be rotating this plane, this red plane, around. And I've made this line so you can see exactly how many degrees it has rotated under the different situations. Then I also have these little cubes here that I've set to be used in a function to set a start angle and end angle, because those are used a lot in games. A lot of times you're going to want to look at something or point your character at something and rotate your character to be pointing at some point in space. So I'll kind of show how to do that too. So let's take a look at the code behind here. So what I've done is on my main camera, I just have a script called rotation demo, and I've exposed a bunch of items out of that script. I have my red plane itself, the two targets, and an end and a middle target, which I ended up not using along this line, and a text output that I'll show a little later when using the Lerp functionality. So to start, we're going to start very simple. And what I'm going to do is every update here, I have this process keys. And what I'm going to use is use the keyboard in order to control the rotation of my object. I like to use the keyboard because you can step in a very controlled fashion. And you know exactly what's going on every time you hit a key. And so what I'm going to do is when I hit the A key, I'm going to take my rotation plane, which is that red plane object. I'm going to take its transform, and I'm going to take the Euler angles and I'm going to modify them. Now, the transform is basically the rotation of the transform is a quaternion. Now, quaternions are very important to understand, and it's a very kind of difficult mathematical concept to understand. Here I've declared a quaternion, again, which is what Unity uses for all of its rotations. Now, there's some videos on quaternions, and I've watched them. It's a kind of a complicated mathematical concept where instead of using angles around the x, y, z coordinates, it uses 4 integer values, one of them being an imaginary number. If you don't know what imaginary numbers are, it's basically the square root of -1, which of course can't exist, which is why it's imaginary. So you can imagine understanding quaternions are kind of hard. It's easier to understand rotations around the x-axis, the y-axis, and the z-axis. And so what Unity has done is it allows you to set the quaternion angles using rotations around the x, y, and z. And that's what the Euler angles do. And it is pronounced Euler angles. I always thought it was Euler angles, but this is named after a guy, Euler, who obviously was some mathematician way back when. But you can set the Euler angle using rotations around the x-axis, the y-axis, and the z-axis. So what I've done here is every time I hit the A key, I'm going to take and I'm going to subtract 10 degrees off of the rotation around the y-axis. Now, if you remember, the y-axis is the one that points up off of our plane. And so it is going to rotate around that axis pointing straight up, and it's going to subtract 10 degrees off of that. Now the question is when you specify a degrees, is the rotation clockwise or counterclockwise? And it really depends on how the function was set up, and I never really know whether it's clockwise or counterclockwise until I try to add or subtract an angle and see which way it moves. In this case, negative is counterclockwise and positive is clockwise. So I'm going to subtract 10 degrees every time I hit the A key. If I hit the D key, I am going to add 10 degrees onto it. And that's pretty much it. So let's go back to our Unity project, and we're going to run it and see what happens. Now you can't see the keyboard that I'm hitting, but I just hit the D key. So every time I hit the D key, it is adding 10 degrees, and you can see that it's rotating 10 degrees every time I hit the key. And I can go all the way around the circle. And one thing to remember is that if I pass 360 degrees, in this case it's now 370 degrees, it is going to just start over again. It's going to always, basically, you can think of it as subtracting 360 degrees if it's over 360 degrees in order to get the angle. So I can keep going around forever hitting the D key, and of course if I hit the A key, it is going to subtract 10 degrees, and I am going to go counterclockwise. All right, easy enough to understand. But that is one way of setting your angle, is if you know a specific angle you want to change, you can simply add or subtract onto the Euler angle of your object you want to rotate. So in many cases, you want to smoothly rotate from where you're currently looking to where the new place that you want to look, right? So you have a character and something enters the scene. You want to now rotate your character to that. You don't want to snap them, meaning you don't want to change it all at once because that doesn't look natural, right? You want to smoothly rotate over time between your current angle where you're looking and where you want to look to. So that's where Lerp and Slerp come in. So what we're going to do is I'm just going to comment out this code, and I'm going to uncomment this code. KU for uncomment. Let's comment out this guy. Let's uncomment out this guy. All right. So now what's going to happen is every time I hit the A key, what it's going to do is it is going to step my current Lerp step by 1/18 of a number. So let's take a look at what Lerp is doing to understand why I'm doing this. So every time I call this function, it's going to pass a step number in. Now this step number is going to be between 0 and 1. So essentially, when I call this Quaternion.Lerp function, it is going to compute a rotation that is somewhere between the start angle and end angle based on a number between 0 and 1. If this number is 0, it will return the start angle. If this number is 1, it will return the end angle. And if it's something in between, it will return an angle somewhere in between that. If this is 0.5, it will return an angle halfway between the start and end angle. So the key here is knowing our start angle and end angle and being able to compute a number between 0 and 1 that transitions between the start and end angle. So what I've done is I have, scroll up here, I have this current Lerp step, which starts at 0. And every time I hit my A key, I am going to subtract 1/18 off of that. So it's essentially, it should step, if my start angle is 0 and my end angle is 180 degrees, it will step 10 degrees. And if you can see here, what I've done is I've set my start angle, I've set the Euler angle for my start to 0 degrees, and my end angle to -180 around the y-axis. So this will cause it to rotate in the counterclockwise rotation. If this was a positive 180, it would rotate, actually positive would rotate counterclockwise, negative rotates clockwise. Again, took me a little trial and error to figure out which way, counterclockwise or clockwise, it would rotate depending on what this number was, because you can reach 180 going either direction. All right, so we got our start and end angles, and we have our current step starting at 0. Each time I hit A, it is going to subtract 1/18. Each time I hit D, it's going to add 1/18. So let's build that. Let's go back to our project. And what I'm going to do also is I have set up some UI components so we can kind of watch our step number. So this number here is going to be what the step number is. And I can toggle between using Lerp and using Slerp. And so we can see what the difference between those two functions are. So we're just using Lerp for now. That's why it says that. All right, so let's run this. And I'm going to hit my D key. So 0.06, that's 1/18. It did not quite reach 10 degrees using Lerp. So if I keep hitting it, you'll notice it hit 90 degrees. So in the middle, when I was halfway between 0 and 1, it did reach 90 degrees. So basically what it's doing is it is slowing down as it gets closer to the end point. And it starts out slower, it speeds up, it reaches the middle, and then it comes around and it slows down again. Again, this is kind of counterintuitive because Lerp is a linear interpretation. But obviously, with using quaternions, a linear number gives you a non-linear rotation as it goes from 0 to 1. I am not 100% sure why, but this little test shows us that. Now, if instead we decide to use the Slerp, which is a non-linear, meaning it is a spherical, meaning if I was to use this on a vector point, it would actually start out slower, speed up in the middle as far as the distance it would travel each time I increase my step, and then slow down at the end. But when using it with Quaternion.Lerp, it actually achieves a linear step. As you can see here, using Slerp, we get a linear step, meaning the step is the same as we go from 0 to 1. So this test kind of helps us visualize and understand what's going on, and that's really important when working with rotations, is you need to be able to visualize what's going on. And by setting up little demonstrations like this, you can really understand the difference between these functions. If you're trying to integrate it into the game right away, it's really hard to see what's going on and understand what's going on. And you really need to understand what is happening when you're changing these step values on your rotations in order to achieve the results that you want. All right. So now what we're going to do is take a look at the code of, instead of hard coding my start angle and end angle to 0 and 180, I am going to start them pointing at my two reference objects. So I expose this target 1 and target 2, which is those two colored cubes. So what I'm going to do is, I have a function down here that says use points. So when I click on that button, use points, it's going to call this function. And what it's going to do is it's going to set the start angle to set look rotation, and it's going to look at the position of that cube. So in this way, I can set my angles, the start angle and end angle, to any 2 points in space. So this is very helpful. Again, if I was looking in one direction and I just wanted to look at another direction, I could start my angle at my current angle, and I could end my angle at what I want to look at. In this case, I'm going to set both the start and end angles to look at two different objects. All right. So let's go back to our Unity project. Let's run it. What I'm going to do is I'm going to click Use Points. You can see as soon as I click that, it now is looking at my first object. So 0 is my start angle, and I'm looking at my first object. And now when I hit D, it's going to step 18 steps. Because remember, really, that step number is just how much you want to rotate between your start angle and end angle. So it's still going to take 18 steps between those because I'm adding 1/18. We can see our numbers toggling up here between the start angle and end angle. All right. So that's very fine when using our keyboard, but that's really not how we're controlling our game object. I mean, maybe we are. Maybe we're taking a mouse import, and maybe we are taking the keyboard import in order to rotate. But we generally want to rotate far smoother than those big steps. So how would we do that? So let's take a look at the last demonstration, and that's this do smooth. So when I click the do smooth button, I'm just going to set this Boolean variable to true. And let's see what happens when that's true. So we have to go up to our update function. So if you remember, every time through the game loop, it's going to call our update many, many times a second. And if I am doing a smooth rotate, what it's going to do is it's going to take our time, the amount of time that happened between the last update, and it's going to multiply by rotation speed. So we can control the speed that I go from 0 to 1 by setting this rotation speed. And really, that is just a value. In this case, I used 0.5 to control that speed. And I'm going to call this do smooth function using my current Lerp step. So what is do smooth going to do for me? So let's go down to that function and take a look. So what it's going to do is it's going to set the rotation using Slerp in this case, because I want to use a more linear application of my steps. But instead of just using this step directly, what I'm going to do is I'm going to feed in that step into a sine function. So why do I want to do this? Well, a lot of times when you're rotating, if you think of you're going to turn to look at something, you have momentum, right? You have to start your motion. You start out turning slowly and then you accelerate. And then as you are getting toward your end angle that you want to rotate, you want to slow down. It makes for smoother rotation. And sine is used in a lot of cases in order to get smooth rotation. So why am I doing this step for pi? We can see that by taking a look at our sine wave to understand a little bit better what this is going to do for us. So what I'm going to do is bring up a picture of a sine wave. So I've Googled sine wave here. And let's look at what it's going to do. So when I feed 0 into a sine wave, it is going to output 0. That's what this is showing. 0 in, 0 out. As I move toward pi over 2, it is going to go up to 1. And remember, we want a number between 0 and 1, which is why the sine wave is perfect for us, because that's what the sine wave does. It moves between 0 and 1, and it slows down, right, this part of the curve as it approaches 1. Then it slowly starts accelerating. Slowly starts accelerating as it passes 1, and then it's going to go back down to 0 when it reaches pi. So what I'm going to do is I'm going to feed my step. Remember, my step is going from 0 to 1. I'm going to multiply it by pi. So when step is 0, it's going to take the sine of 0. When step is 1, it is going to take the sine of pi. And when it's 0.5, it's going to be pi over 2. So when it's pi over 2, the output will be 1. So what should happen is this step in this function is going to go from 0 to 1 and then back to 0 again. So let's take a look at our Unity. Let's run it. And now let's click smooth and see what happens. So you can see what happened is it started out slowly. It accelerated as it passed 90 degrees. It slowed down as it reached 180, and then it started to reverse and go back to 0. So if we just did this linearly, went here, stopped, and then reversed, what it would look like is would look like it bounces off of this stop point, which a lot of times is not what we want. It doesn't look natural. So using sine and feeding a step number into that sine function can really help give you better, smoother rotations. And remember, you don't have to start at 0. If I added pi over 2, I would start here. I could just travel from here to here by modifying my output. Remember, as soon as it passes 1, it goes into the negative territory, so I may not want that. But by manipulating my input, I can pick my 0 to 1 to go anywhere on this sine graph, which again is very handy when getting smooth rotations. So the last thing I'm going to do is show just a straight linear from 0 to 1. So if we look at our input keys, if I hit the S key, I'm just going to set auto rotate to true. And when that's true, what I'm going to do is I'm simply going to either use Lerp or Slerp and change my current Lerp step simply by the delta time rotation speed. So instead of feeding it into that function using the sine wave, I'm just going to do a linear rotation. So let's go back to here, and I'm using Lerp. I'm going to run this. I'm going to hit the S key, and you can see it's slowly counting from 0 to 1. Just going to hit it again in a linear fashion and is going to rotate. If I click use Slerp, try it again, you really don't see a lot of difference. Again, that Lerp and Slerp, I don't see a lot of difference. You can kind of see it kind of starts out slower and speeds up and slows down, but it's not a really big difference. It's not as big a difference as when we use the sine wave in order to modify our numbers between 0 and 1. So, to recap, the key to using Lerp and Slerp are really understanding how to change this step value between 0 and 1 in a way that achieves the look of your rotation that you want, and understanding how to create your start angle and end angle. So it takes a lot of playing around with this, and again, using a sample setup like I've set up really helps you visualize what's going on. And once you understand what's going on, you can now integrate this functionality into your games in a way that achieves the results you want. So I hope this helped you understand rotations. I'm going to do a follow-up tutorial on understanding how to apply this in a localized plane, because all the numbers we've been dealing with here are in global coordinate system, and in a lot of times you need to convert these rotations into a local coordinate system. So I'll be doing another tutorial on how to do that. If you found this useful, give it a thumbs up, and I have lots of other tutorials on my channel, so subscribe to my channel and check out the other videos.